In the darkness of space, there are ghostly remnants of dead stars, mysterious signals that whisper secrets of other worlds, and violent collisions of black holes. Each story reveals a hidden piece of a universe that is as spectacular as it is eerie. You'll find yourself drawn into tales of space debris spiraling in a deadly dance, stars that come back to life like forgotten memories, and other ideas that seem straight out of movies. So just relax and let your mind wander among these cosmic wonders. The universe's relentless expansion, drifting toward an inevitable void. Since the Big Bang, space itself has stretched outward, carrying galaxies, stars, and entire clusters along with it. For much of human history, the night sky seemed eternal and unchanging. Even as astronomers studied the heavens and discovered the vastness of the cosmos, they assumed it was stable. But in reality, the universe is not just expanding, it is accelerating, moving toward a fate where all matter drifts into an empty, dark void. For decades, scientists debated how the universe's expansion would unfold. The force of gravity, pulling everything inward, seemed to suggest that the expansion would slow over time. If there was enough mass, the universe might even reverse course, collapsing in on itself in a big crunch. Alternatively, it could expand forever at a constant rate, gradually thinning out, but never truly stopping. But in the late 1990s, these expectations were shattered. Astronomers studying distant supernovae found that galaxies were not just moving away from each other, they were doing so at an ever-increasing rate. Something was pushing them apart, working against gravity in a way never before observed. This force, now known as dark energy, was not just influencing the universe, it was dominating it. Unlike matter, dark energy does not clump together or form structures. Instead, it is woven into the very fabric of space, stretching it outward, faster and faster. And the more space expands, the stronger this force seems to become. At first glance, this change is almost imperceptible. Galaxies appear frozen in place over a human lifetime. But across billions of years, the consequences are profound. As the universe stretches, galaxies become more distant from one another. The farther away they are, the faster they recede. Beyond a certain point, they move so quickly that their light will never reach us, crossing what scientists call the cosmic event horizon. They become lost to us forever, as if they never existed at all. This means that the observable universe is shrinking, not in size, but in what we can ever hope to see. The deep space that astronomers study today, filled with galaxies and cosmic structures, will become a lonely void. Future civilizations, if they exist, may look into the sky and see only their own galaxy. They will have no evidence that anything else was ever out there. The signs we use today, distant light, cosmic background radiation, echoes of the Big Bang, will fade away, leaving only darkness. The acceleration of expansion has dire consequences for the universe's long-term future. As time stretches forward, the vast galaxy clusters that now define the cosmos will unravel. Gravity will no longer be able to keep them together. Stars within galaxies will drift apart, eventually losing their ability to form new generations of stars. Over unimaginable timescales, even the brightest galaxies will fade into blackness as their stars burn out one by one. The grand structures of the universe, once filled with vibrant activity, will become cold and lifeless. But the process does not stop there. If dark energy continues to accelerate the universe's expansion, there may come a time when even reality itself is pulled apart. Known as the Big Rip scenario, this possibility suggests that in the final moments of the universe, space will stretch so violently that it will tear down everything: stars, planets, and even atoms. The fundamental building blocks of matter may be ripped apart, dissolving into an incomprehensible nothingness. Even in less extreme scenarios, the fate of the universe is grim. If expansion continues at a steady rate, it will eventually reach a point where only black holes remain, the last gravitational strongholds in an otherwise empty cosmos. Over trillions upon trillions of years, black holes slowly evaporate due to a process known as Hawking radiation. So, one by one, they too will vanish, releasing their final energy into the void. At that point, nothing will remain. No galaxies, no stars, no planets, just a vast empty space stretching endlessly in every direction. This is the universe's ultimate destiny, dictated by the very laws of physics that allowed it to form in the first place. The same forces that created galaxies, stars, and life itself are also ensuring that one day everything will be gone. In the end, the cosmos will be nothing more than a cold, silent void. Vanishing moons, the silent disappearance of celestial bodies. Moons have always been a familiar presence in the cosmos. They orbit planets, influencing tides, stabilizing rotations, and sometimes even serving as potential habitats for life. But while many of them have remained in place for billions of years, others have mysteriously vanished. Some were torn apart by the gravitational forces of their parent planets. Others were flung into space, and some may have simply crumbled over time. One of the most well-known cases of a vanishing moon is the loss of Mars's hypothetical ancient satellites. Today, Mars has two small, irregularly shaped moons, Phobos and Deimos, but evidence suggests that it may have once had larger moons. Some researchers believe these moons formed when a massive asteroid or another planetary body collided with Mars in the distant past, sending debris into orbit. Over time, some of this debris coalesced into moons, while other fragments likely fell back to the planet or drifted away. If larger moons once orbited Mars, they may have eventually spiraled inward, drawn closer and closer by gravitational interactions, until they were torn apart by tidal forces. Their remains would have either crashed into the planet or formed temporary rings before dispersing. Phobos itself is on a path toward destruction. Unlike Earth's moon, which is slowly drifting away, Phobos is moving closer to Mars. Each year, it edges a little nearer, and scientists estimate that in 30 to 50 million years, it will either collide with Mars or break apart due to gravitational forces. If it shatters, the debris could form a ring around the planet, one that would be short-lived on cosmic timescales. Eventually, the dust and rock would either rain down on Mars or disperse into space, leaving no trace that Phobos ever existed. Beyond our solar system, moons may vanish without a trace due to the chaotic nature of planetary systems. Some exoplanets orbit so close to their stars that any moons they once had may have been lost. The intense gravitational forces of the star and planet could destabilize a moon's orbit, either pulling it into the planet or ejecting it entirely. In some cases, these moons may be drawn into the star itself, where they are swallowed without a sign. Detecting these missing moons is nearly impossible. Unlike planets, which can block starlight when they pass in front of their stars, moons are too small to create noticeable effects from vast distances. They disappear without leaving any obvious evidence behind. Some moons may be destroyed in violent cosmic events. A collision between two planets or large asteroids can generate enough force to shatter a moon completely. The debris may form a new moon, create a ring system, or be scattered across space. A similar event may have occurred in our own solar system long ago. Saturn's impressive ring system, composed of ice and rock, may be the remnants of a destroyed moon. One theory suggests that an ancient moon of Saturn spiraled too close to the planet and was torn apart by tidal forces. Instead of falling into the planet, its shattered remains spread out, forming the rings we see today. Over time, these rings will thin out and disappear, erasing the last traces of the moon that once existed. In a far-off future where human civilizations expand into the solar system, artificial satellites and large-scale engineering projects might disrupt the delicate gravitational balance that keeps moons in place. A miscalculation or an attempt to mine a moon for resources could send it spiraling out of orbit. Even a small push in the wrong direction could have long-term consequences, leading to the moon's eventual ejection or destruction. The universe is constantly reshaping itself, breaking apart celestial bodies as easily as it creates them. No moon is guaranteed to remain in orbit forever. Their disappearance is yet another sign of the universe's slow and inevitable transformation, where even the most familiar objects can quietly fade into the darkness. Kessler syndrome, the self-destructive cascade of space debris. The space surrounding Earth has over time been filled with thousands of artificial satellites, discarded rocket stages, and countless fragments of debris from past missions. For decades, humans have been launching objects into orbit, and with each mission, more pieces of equipment are left behind. Some of these objects remain operational, providing essential functions like communication, weather tracking, and scientific observation. Others are long since defunct, lifeless husks of metal floating in space with no purpose. But every one of these objects, active or abandoned, shares the same environment. They travel at astonishing speeds, reaching velocities of more than 28,000 kilometers per hour. At these speeds, even something as small as a paint chip can cause serious damage. A single loose bolt could tear through a satellite or spacecraft like a bullet, and larger objects could cause catastrophic destruction if they were to collide. Over the years, the buildup of space debris has become one of the most pressing concerns in space exploration. Every launch, every satellite, and every collision adds to the growing swarm of objects in orbit. As more material accumulates, the likelihood of crashes increases. When two objects collide, they do not simply bounce off each other. Instead, they shatter into countless smaller fragments, each of which becomes a new threat. These fragments, in turn, can collide with other objects, creating even more debris in a dangerous chain reaction. This process is known as Kessler syndrome, a theory first proposed by NASA scientist Donald Kessler in 1978. According to this model, once the number of objects in orbit reaches a certain threshold, the rate of collisions could spiral out of control, leading to an exponential increase in space debris. The consequences of this scenario are far-reaching. If enough debris fills low Earth orbit, it could make space travel nearly impossible. Communication satellites, which provide internet access, weather monitoring, and GPS navigation, could be damaged or destroyed. The International Space Station, or ISS, would be at constant risk of impact. Future space missions, including plans for a return to the Moon or a journey to Mars, could be jeopardized by the overwhelming danger posed by high-speed debris. In the worst-case scenario, Kessler syndrome could trap humanity on Earth for generations, making space too hazardous to explore. Collisions have already started. One of the most well-documented cases occurred in 2009, when a defunct Russian satellite, Cosmos 2251, slammed into an active American communications satellite, Iridium 33. The impact obliterated both satellites, producing thousands of pieces of debris. Some of these fragments remain in orbit today, forming a deadly cloud of high-speed shrapnel. In 2007, China conducted an anti-satellite missile test, deliberately destroying one of its own aging satellites. The explosion added over 3,000 pieces of debris to Earth's orbit. Each of these fragments became a potential hazard for other satellites, increasing the overall risk of future collisions. The ISS has already faced multiple threats from space debris. In some cases, astronauts have been forced to take shelter in emergency escape vehicles as a precaution against incoming fragments. In other instances, mission control has had to adjust the station's orbit to avoid dangerous debris fields. These maneuvers require precise calculations and significant amounts of fuel, and as space debris continues to accumulate, such measures may become even more frequent. Unlike natural threats in space, such as asteroids or solar radiation, Kessler syndrome is a crisis of our own making. It is a direct result of human activity, and with each passing year the problem grows worse. Governments, space agencies and private companies are well aware of the issue, but finding a solution is not easy. Many proposals have been suggested, ranging from robotic arms that can capture and remove large pieces of debris to lasers that could push fragments into lower orbits, causing them to burn up in Earth's atmosphere. Other ideas involve deploying nets, harpoons, or even spacecraft designed specifically to remove debris from orbit. While these concepts are promising, none have been fully implemented on a large scale. At the same time, new satellites are being launched at an unprecedented rate. Companies like SpaceX, Amazon and OneWeb are deploying vast networks of satellites to provide global internet coverage. These projects, while technologically impressive, add even more objects to the already crowded orbital environment. Some experts worry that if proper regulations are not put in place, the rapid expansion of satellite networks could accelerate the onset of Kessler syndrome. One of the biggest challenges in dealing with space debris is that it is nearly impossible to track every single object. Large satellites and rocket stages are monitored closely by space agencies, but smaller fragments, especially those no larger than a screw or a piece of metal, are much harder to detect. Yet these tiny objects can still cause significant damage. A collision with a small piece of debris could disable a satellite, knocking it out of commission and creating even more fragments. The more objects there are, the harder it becomes to predict and prevent further collisions. Many of the technologies we rely on every day depend on satellites. GPS, weather forecasts, financial transactions, and even emergency response communications all rely on space-based infrastructure. If satellite networks were to be disrupted by debris, it could have wide-ranging effects on life here on Earth. Efforts to reduce the risks of Kessler syndrome must go beyond simply cleaning up debris. Preventative measures are equally important. Engineers are developing satellites that can deorbit themselves at the end of their missions, either by using onboard propulsion systems or by deploying large sails that increase atmospheric drag. Some organizations are advocating for stricter regulations on satellite launches, requiring companies to take responsibility for the long-term impact of their missions. Without these kinds of measures, the situation could become unmanageable. Unlike natural cosmic phenomena that unfold over millions or billions of years, Kessler syndrome is developing on a human timescale. Within a matter of decades, the growing cloud of orbital debris could reach a point where space becomes too dangerous for human missions. The vastness of space once seemed limitless, but low Earth orbit is becoming increasingly crowded. As the number of objects in orbit continues to rise, humanity faces an urgent question. Will we take action to prevent a cascading catastrophe? Or will we allow the consequences of our own technology to lock us out of space forever? Black hole merges when darkness devours itself. Black holes usually exist alone, silently consuming anything that gets too close, but sometimes they meet their equals. When two black holes drift close enough, their immense gravity pulls them into a spiraling dance that leads to one of the most extreme events in the cosmos, a black hole merger. As the two black holes draw nearer, they begin to orbit one another. This motion is violent and chaotic, generating ripples in the fabric of space and time. These ripples are known as gravitational waves, and they spread outward from the merging black holes, traveling across the universe at the speed of light. Though these waves are nearly imperceptible by the time they reach Earth, they carry with them the signatures of cosmic cataclysms from millions or even billions of years ago. Gravitational waves were first predicted by Albert Einstein over a century ago as part of his theory of general relativity. He described how massive objects bend space and time, much like a heavy ball placed on a stretched sheet of fabric. If the object moves, it sends out ripples in the fabric, just as black holes do when they orbit and merge. For decades, these waves remained a theoretical concept. That changed in 2015 when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected them for the first time. The signal came from two black holes, each dozens of times more massive than the Sun, colliding over 1 billion light-years away. The final moments before the merger are the most intense. As the black holes spiral toward each other, they accelerate, moving at speeds close to the speed of light. The gravitational waves they emit become stronger, creating a crescendo that scientists call the chirp. At the peak of this process, the two black holes collide and merge into a single, larger black hole. In an instant, a tremendous amount of energy is released, not in the form of light, since black holes do not emit light, but through the gravitational waves that ripple across the cosmos. The black hole left behind from the merger is different from either of its parents. It is larger, but not as massive as the combined total of the two original black holes. Some of their mass is converted into energy, following Einstein's famous equation E equals mc squared. This means that during a merger, a portion of the black hole's material is lost, turned into pure energy that radiates outward in the form of gravitational waves. These waves, though faint by the time they reach Earth, carry the history of these massive collisions, allowing scientists to detect and study events that took place long before humanity even existed. In the vastness of space, black hole mergers occur frequently, but because they do not produce light, they remain hidden from traditional telescopes. It was only with the development of gravitational wave detectors that scientists began to uncover just how common these collisions are. Since LIGO's first detection in 2015, dozens of mergers have been recorded, each one revealing new details about black holes and the forces that govern them. Some black holes are formed from the deaths of massive stars. When a star much larger than the Sun exhausts its fuel, it collapses under its own gravity, forming a black hole. If two such stars are born close together, they may orbit one another for millions of years. Over time, they gradually lose energy, spiraling closer until they merge. But not all mergers happen this way. In the dense environments of star clusters or near the centers of galaxies, black holes can form and interact in chaotic ways. Some may be flung away, while others are drawn together by gravity. At the centers of galaxies, much larger black holes lurk. These supermassive black holes, millions or even billions of times the mass of the Sun, can also merge. When galaxies collide, their central black holes are pulled toward each other, beginning a slow, inexorable dance that can last for millions of years. These behemoths create gravitational waves with even more energy, though their collisions have yet to be directly detected. Future observatories designed to sense even longer wavelength gravitational waves may one day allow us to witness the merging of supermassive black holes in distant galaxies. As black holes merge, they send out bursts of gravitational energy that stretch and squeeze space itself. If two merging black holes are not perfectly aligned, the newly formed black hole can be sent hurtling across the galaxy. This phenomenon, known as a recoil kick, occurs when the merger produces an imbalance in the gravitational wave emission, effectively giving the new black hole a push. Some kicked black holes may be ejected from their home galaxies entirely, doomed to drift alone through intergalactic space. Unlike light-based astronomy, which relies on detecting electromagnetic radiation, gravitational wave astronomy allows scientists to listen to the universe in a way never before possible. Every new detection adds to our understanding of these objects, confirming theories, revealing unexpected behaviors, and helping us map the population of black holes across the cosmos. Gamma-ray bursts, the universe's lethal flashbulbs. For a few fleeting moments, gamma-ray bursts release more energy than an entire galaxy, lighting up the cosmos with an intensity so great that they can be detected from billions of light years away. These bursts are so short-lived that they are over in seconds, yet their impact can stretch across vast cosmic distances, delivering high-energy radiation capable of stripping atmospheres from planets and disrupting entire star systems. They are the flashbulbs of the universe, sudden and blinding, leaving behind only remnants of their destructive power. Gamma-ray bursts come in two main types, long and short. The long bursts, which last more than 2 seconds, are believed to be caused by the collapse of massive stars. When a large star's core collapses and it forms a black hole, the surrounding material falls inward, generating enormous amounts of energy. Some of this energy escapes in the form of powerful jets, traveling nearly at the speed of light. If one of these jets is aimed in Earth's direction, it appears as a blinding flash of gamma rays, outshining everything else in the universe for that brief moment. The short bursts, lasting less than 2 seconds, are thought to come from the merger of two neutron stars, or a neutron star and a black hole. When these incredibly dense objects collide, they send shockwaves through space-time, generating a burst of gamma rays before collapsing into a singularity. A typical gamma-ray burst can release as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifespan. Unlike supernovae, which unfold over days or weeks, these bursts are instantaneous, detonating with a force that can be seen across the universe. Their short duration makes them difficult to study, as they appear and disappear before telescopes can properly focus on them. Most gamma-ray bursts are detected by satellites designed to monitor high-energy radiation, which immediately alert astronomers when a new burst occurs. Within seconds, observatories around the world turn their attention to the explosion, trying to capture as much information as possible before it fades. The after-effects of a gamma-ray burst can linger for minutes, hours, or even days, depending on how much energy was released. The visible light, X-rays, and radio waves produced in the explosion's aftermath help astronomers determine where the burst originated and what caused it. By studying these afterglows, scientists have confirmed that many long-duration bursts come from galaxies forming new stars, while short-duration bursts often occur in regions where dense objects like neutron stars are found. Some of these bursts have been traced back to the farthest reaches of the universe, meaning they occurred billions of years ago, when the cosmos was still young. If a burst were to occur close to Earth, its high-energy radiation could strip away the planet's protective ozone layer, exposing the surface to deadly ultraviolet radiation from the Sun. This could trigger mass extinctions, wiping out species and disrupting ecosystems in ways that would take millions of years to recover from. Some scientists have suggested that a past gamma-ray burst may have been responsible for at least one mass extinction event on Earth. While such an event is rare, the sheer power of these bursts makes them one of the most destructive forces in the universe. They influence the formation of black holes, distribute heavy elements across space, and may even contribute to the cosmic rays that travel through the universe at nearly the speed of light. The extreme environments that produce these bursts push the laws of physics to their limits, offering insights into how matter behaves under the most extreme conditions imaginable. Despite their destructive nature, gamma-ray bursts also reveal the vast scale of the universe. Some of the brightest bursts ever recorded originated from galaxies so distant that their light has been travelling for over 13 billion years. These bursts act as beacons from the early universe, providing a glimpse into a time when the first stars and galaxies were forming. By analysing the light from these bursts, astronomers can study the conditions of the universe when it was only a fraction of its current age. The mechanisms behind gamma-ray bursts are still not fully understood. Some bursts seem to defy existing models, emitting radiation in patterns that challenge current theories of how energy is released in extreme environments. In some cases, bursts appear to come from locations where no obvious source, such as a collapsing star or merging neutron stars, can be found. These mysterious bursts suggest that there may be other, yet undiscovered processes at work. Observations of gamma-ray bursts have also led to discoveries beyond the bursts themselves. In studying their afterglows, astronomers have detected distant galaxies that were previously too faint to see. Some bursts have revealed the presence of heavy elements in intergalactic space, shedding light on how these materials spread across the cosmos. The study of gamma-ray bursts has also helped refine measurements of the expansion rate of the universe, offering another way to test theories about dark energy and the ultimate fate of the cosmos. With more advanced instruments, scientists hope to capture bursts in greater detail, revealing the precise mechanisms behind their energy release. Some missions aim to detect bursts even farther away, probing the first few 100 million years after the Big Bang to understand how the earlier stars lived and died. Others will focus on the connections between gamma-ray bursts and gravitational waves, studying how these two cosmic signals interact when massive objects collide. Their unpredictability, combined with their sheer power, makes them one of the most fascinating and fearsome phenomena in the cosmos. The flashes they produce may be brief, but their echoes reveal secrets of the cosmos that might otherwise remain hidden. The ghostly shockwaves of supernova remnants. When a massive star reaches the end of its life, it undergoes a cataclysmic explosion called a supernova. But while the explosion itself lasts only a brief moment, its effects ripple through the cosmos for thousands, sometimes even millions of years. The shockwaves left behind by these stellar deaths continue to move outward, carving through space and shaping the surrounding regions long after the initial blast has faded from sight. These shockwaves expand outward at incredible speeds, sometimes reaching tens of thousands of kilometers per second. As they move, they sweep up interstellar gas and dust, creating vast shells of heated material. This expanding debris, known as a supernova remnant, glows with an eerie light illuminated by the energy of the explosion. Some of these remnants appear as thin, glowing filaments stretched across the darkness, while others form great billowing clouds that continue to expand for thousands of years. One of the most well-known supernova remnants is the Crab Nebula, the remains of a supernova that was observed by astronomers in the year 1054. What remains of that explosion is a tangled structure of glowing filaments and expanding gas, still racing outward at high speeds. At its heart lies a rapidly spinning neutron star or pulsar, which continues to emit pulses of radiation as it spins dozens of times per second. The energy released by the pulsar interacts with the surrounding gas, keeping the nebula glowing long after the initial explosion. Not all supernova remnants are as well defined as the Crab Nebula. Some fade into ghostly structures, their expanding shockwaves becoming more difficult to detect as they spread out over time. Others remain visible for tens of thousands of years, their shells of gas colliding with nearby clouds of interstellar material. When this happens, the shockwaves can compress the gas, triggering the birth of new stars. In this way, the death of one star can lead to the creation of others, continuing the endless cycle of stellar evolution. These shockwaves also play an important role in distributing heavy elements throughout the universe. The immense energy of a supernova fuses atoms together, creating elements like iron, gold, and uranium. When the explosion occurs, these materials are scattered into space, becoming part of the dust and gas that will eventually form new planets. Every heavy element on Earth, including those found in our bodies, was once forged in the heart of a dying star and sent into space by a supernova's shockwave. Some of these remnants remain energetic for thousands of years, glowing in X-rays and radio waves long after the visible light has faded. The Veil Nebula is a supernova remnant located about 2,100 light-years away. The explosion that created it occurred roughly 10,000 years ago, yet its structure is still expanding, with tendrils of glowing gas stretching across an area of space large enough to hold dozens of full moons. The nebula is so vast that different parts of it are given separate names, including the Eastern Veil, the Western Veil, and Pickering's Triangle. The way these remnants interact with their surroundings depends on the density of the interstellar medium. In regions where gas and dust are abundant, the shockwaves create intricate and detailed structures, forming wispy filaments and dense knots of glowing material. In emptier regions of space, the shockwaves can travel for much longer distances, expanding in smooth, spherical shells that eventually become so thin they blend into the surrounding void. Some remnants remain visible due to the radiation they emit. As the shockwaves plough through interstellar gas, they heat it to millions of degrees, causing it to glow in X-ray and radio wavelengths. These emissions allow astronomers to track the expansion of supernova remnants even when they can no longer be seen with the naked eye. Observations in these wavelengths have revealed that some remnants are still expanding at high speeds, while others have slowed down as they encounter denser material. In rare cases, supernova remnants collide with other remnants, creating complex shockwave interactions that shape the structure of the surrounding space. When two or more shockwaves meet, they can create turbulent regions where high-energy particles accelerate, producing intense bursts of radiation. These interactions are believed to be responsible for some of the highest energy cosmic rays detected on Earth. Supernova remnants stir up the interstellar medium, enriching it with heavy elements and triggering new waves of star formation. Without them, the universe would lack many of the materials necessary for planets, life, and even the complex chemistry that makes human existence possible. Every atom of iron in our blood, every trace of gold in the Earth's crust, and every bit of oxygen we breathe was once part of a distant star that exploded long ago. The structures they leave behind may persist for tens of thousands of years, but over time, the energy disperses and the glowing filaments vanish into the darkness. In the end, all that remains are the stars and planets that formed in the wake of these explosions, continuing the cycle that has shaped the universe for billions of years. The deep space radio signals with no known origin. Deep in space, strange and powerful radio signals have been detected, pulsing from unknown sources. These signals come from distant regions of the universe, traveling for millions or even billions of years before reaching Earth. Some of them repeat in predictable patterns, while others appear only once, never to be heard again. Despite years of study, their exact origin remains one of the great unsolved mysteries of modern astronomy. The first of these signals was discovered in 1967 by Jocelyn Bell Burnell, a graduate student working on a new type of radio telescope. She detected a strange, rhythmic signal that pulsed every 1.33 seconds, unlike anything seen before. At first, some astronomers considered the possibility that it might be an artificial signal, perhaps even a message from an intelligent civilization. The discovery was even given the name LGM-1, short for Little Green Men. However, further study revealed that the signal came from a highly magnetized, rapidly rotating neutron star, which became known as a pulsar. If pulsars were capable of producing such strong radio emissions, what other unknown objects might be doing the same? Over the decades that followed, astronomers continued to detect unexplained radio signals. Some were similar to pulsars, but behaved in unusual ways, while others seemed completely different from any known source. One of the most famous unexplained signals is the WOW signal, detected in 1977 by a radio telescope at Ohio State University. It lasted for 72 seconds and was incredibly strong, appearing to come from a point in the sky with no known stars or planets nearby. Astronomer Jerry Ehman, who discovered it, was so struck by its intensity that he wrote the word WOW in the margins of the data printout. Despite repeated searches, the signal was never detected again, and its origin remains unknown. More recently, astronomers have discovered a new class of mysterious signals called fast radio bursts, or FRBS. These powerful bursts of radio waves last only a few milliseconds, but release as much energy as the sun emits in an entire day. The first FRB was discovered in 2007, hidden within old telescope data. Since then, hundreds have been detected, some coming from billions of light years away. Unlike pulsars, which rotate at a steady rate, FRBs appear suddenly and without warning. Some repeat, while others flash once and vanish forever. Some scientists believe they might be produced by magnetars, a rare type of neutron star with an extremely strong magnetic field. Others suggest that they could come from colliding black holes, or even the evaporation of tiny primordial black holes formed in the early universe. Some FRBs seem to originate from galaxies with active star formation, while others come from old, quiet regions of space. This variety makes it difficult to pinpoint a single explanation for all of them. One of the most intriguing repeating FRBs, known as FRB 121102, was found in 2012. Unlike most FRBs, which appear only once, this one flashes repeatedly from the same location, a small, distant galaxy more than 3 billion light-years away. Over time, scientists have recorded hundreds of bursts from this source, making it the first FRB with a confirmed location in the universe. Later, other repeating FRBs were found, each with their own unique patterns. Some follow a cycle, flaring up for a few days and then going silent for weeks or months. Others burst unpredictably, with no apparent pattern at all. If FRBs were caused by cataclysmic events like neutron star collisions, they should not repeat. Some astronomers suggest that they might be coming from highly active magnetars in distant galaxies, while others propose that they could be produced by interactions between neutron stars and black holes. Some speculate that a few FRBs might be artificially created, possibly by advanced extraterrestrial civilizations using powerful radio beams for communication or propulsion. One case that fueled speculation was the detection of a mysterious radio signal in 2019 by the Breakthrough Listen project, an initiative designed to search for alien transmissions. The signal, named BLC-1, appeared to come from the direction of Proxima Centauri, the closest star to the Sun. Unlike known astrophysical sources, it was a narrowband signal, similar to those used in human-made radio communications. However, after months of investigation, scientists determined that it was likely a product of interference from Earth-based technology, rather than an actual alien transmission. Despite the lack of confirmed extraterrestrial signals, the study of deep space radio emissions continues to uncover new mysteries. One of the most recent discoveries is the detection of odd radio circles, or ORCs, first observed in 2019. These enormous circular structures appear in radio wavelengths, but have no visible counterpart in optical or X-ray light. They are unlike anything seen before, and their true nature remains unknown. Some scientists suggest they might be shock waves from past galactic collisions, while others propose they could be remnants of powerful explosions within supermassive black holes. The hunt for these unexplained radio signals has provided valuable insight into the universe, revealing hidden objects and energetic processes that would otherwise remain invisible. Pulsars have become important tools for studying the fabric of space-time, while FRBs offer a new way to probe the structure of intergalactic space. By studying how these signals interact with the matter they pass through, scientists can learn about the distribution of gas and magnetic fields across billions of light-years. The square-kilometre array, currently under construction, will be one of the most powerful radio telescopes ever built. It will be capable of detecting faint signals from the earliest days of the universe, possibly uncovering new types of radio emissions that have never been seen before. The Kime telescope in Canada has already made breakthroughs in detecting FRBs, increasing the number of known bursts dramatically. Future missions, such as NASA's planned LUVOIR telescope, may also help in the search by detecting signals in multiple wavelengths, providing more clues about their origins. Whether they originate from neutron stars, black holes, or something yet to be imagined, these signals offer a glimpse into the unseen forces shaping the cosmos. With every new signal detected, the story of the universe becomes a little more complex. X-ray flares from the galactic center, echoes of a star's death. The central black hole of our galaxy, known as Sagittarius A star, is a giant, containing about 4 million times the mass of the Sun. Normally, it is relatively quiet compared to the hyperactive black holes at the centers of some other galaxies. It does not consume large amounts of matter regularly, and for the most part it remains in a dormant state. However, sometimes it awakens. When this happens, astronomers detect sudden spikes in X-ray emissions, brief but intense flashes that reveal an event of extraordinary violence. These X-ray flares are thought to be the result of material falling toward the black hole. When a star or a gas cloud drifts too close, the immense gravitational pull of Sagittarius A star tears it apart. The shredded remains form a spiraling disk of material known as an accretion disk, which heats up to millions of degrees as it swirls toward the event horizon. The extreme temperatures produce high-energy radiation, particularly in the form of X-rays. One of the most remarkable observations of this kind occurred in 2013, when NASA's Chandra X-ray Observatory recorded an unprecedented spike in X-ray activity from the galactic center. Normally, Sagittarius A star produces small flares a few times a day, but this one was hundreds of times brighter than usual. The sudden surge in energy left astronomers searching for an explanation. Some suggested that a small asteroid or planet had been caught in the black hole's grip and vaporized. Others believed that the black hole had devoured a dense clump of gas, temporarily feeding its hunger before returning to a state of relative dormancy. Not all X-ray flares from the galactic center come directly from the black hole itself. Some originate from the interactions of other extreme objects in the same region. Neutron stars and white dwarfs, remnants of long-dead stars, sometimes produce flares as they siphon gas from companion stars. Magnetars can also release sudden, energetic bursts of X-rays when their magnetic fields shift and crack the surface of the star in a process known as a starquake. Another major source comes from the remnants of stars that were once massive enough to supernovae. When such an explosion occurs near the galactic center, it leaves behind shock waves that continue to move through space, heating up gas clouds, causing them to glow in X-ray light. Some of the flares observed near Sagittarius A star may actually be echoes of supernovae that occurred long ago, their radiation only now reaching our telescopes. The most dramatic form of stellar death near the galactic center occurs when a star strays too close to the supermassive black hole and is torn apart in what is known as a tidal disruption event. Unlike a normal supernova, which is a sudden explosion, a tidal disruption event unfolds over a longer period of time as the gravitational forces of the black hole stretch and rip the star apart. The resulting stream of gas spirals around the black hole, creating a temporary surge in brightness. Some of the matter is pulled directly into the event horizon, disappearing forever, while the rest is ejected back into space in a dazzling display of energy. These events provide a rare opportunity for scientists to study black hole feeding behavior in real time. By observing the changes in X-ray brightness and energy levels, researchers can learn about the properties of both the doomed star and the black hole itself. They can determine how much mass the black hole gains during such an event, how fast it spins, and how matter behaves in the extreme gravitational environment near the event horizon. Some astronomers believe that Sagittarius A star may have gone through a feeding frenzy several million years ago, devouring large amounts of gas and dust. The evidence for this comes from enormous X-ray bubbles extending far above and below the Milky Way's disk, known as the Fermi bubbles. These massive structures, discovered in 2010, suggest that the black hole was far more active in the past than it is today. Other galaxies also contain supermassive black holes, and many of them are much more active than ours. The cores of some galaxies produce continuous streams of X-ray and other high-energy radiation, fueled by the constant inflow of matter. In cases where two galaxies are merging, their central black holes can interact, producing even more violent and erratic bursts of energy. Some of the latest studies suggest that the flares may not always be the result of large-scale destruction. Instead, some could be triggered by the complex magnetic fields surrounding the black hole, which may twist and reconnect in ways that release sudden bursts of energy. This process, known as magnetic reconnection, is similar to what happens on the Sun during solar flares, but on a much larger and more powerful scale. Though we can only observe from a distance, these fleeting flashes of high-energy radiation offer a glimpse into the chaotic, hidden heart of our galaxy. Cosmic cannibalism, when galaxies feast on their own. Across the vast stretches of the universe, galaxies drift and move under the influence of gravity, sometimes coming close enough to interact in violent ways. In many cases, larger galaxies consume smaller ones, pulling them apart and absorbing their stars, gas, and dust. This relentless process, often referred to as galactic cannibalism, is one of the driving forces shaping the universe. The Milky Way is not innocent in this cosmic feast. Over billions of years, it has devoured multiple smaller galaxies, leaving behind trails of stars that once belonged to separate systems. Some of these remnants still linger, visible as faint stellar streams stretching across the night sky. One such example is the Sagittarius dwarf galaxy, a small galaxy that has been steadily ripped apart by the Milky Way's gravitational pull. With each passing million years, more of its stars are scattered, blending into the growing spiral of our galaxy. Sometimes the gravitational struggle lasts for billions of years. A small galaxy, drawn toward a larger one, can orbit its predator multiple times before finally being torn apart. The gravitational forces stretch and distort the smaller galaxy, causing its stars to scatter into long streams that wrap around the host galaxy like ghostly tendrils. These remnants offer clues to the Milky Way's past meals, allowing astronomers to piece together the history of galactic mergers. But the Milky Way itself is also on a collision course. In about 4 billion years, it will come face to face with Andromeda, the largest galaxy in the local group. Andromeda, which is currently over 2 million light-years away, is moving toward us at a speed of roughly 110 kilometers per second. This meeting will not be a simple head-on crash, but a slow-motion merger that will unfold over billions of years. Stars from both galaxies will be thrown into new orbits, gas clouds will collide and ignite bursts of star formation, and the supermassive black holes at the centers of both galaxies may eventually merge. Individual stars within these galaxies are separated by such vast distances that direct collisions between them are extremely rare. Instead, the gravitational reshuffling of stars and gas is the primary consequence. As the two galaxies interact, they trigger the birth of new stars, lighting up the darkness with brilliant bursts of energy. When the dust settles, the two galaxies will have formed an entirely new structure, likely a single massive elliptical galaxy, different from either of its predecessors. Across the universe, galaxies of all sizes experience similar fates. Some of the largest galaxies we see today, known as giant elliptical galaxies, likely formed through the repeated consumption of smaller galaxies. These behemoths, found in the dense environments of galaxy clusters, have grown fat on a steady diet of smaller neighbours. Their smooth, featureless appearance suggests that they have undergone numerous mergers, erasing the spiral structures that once defined them. In some cases, galactic cannibalism is more violent. When two gas-rich galaxies merge, their interaction can lead to extreme star formation, creating what is known as a starburst galaxy. The pressure and turbulence caused by the collision compress gas clouds, leading to the rapid birth of new stars. Some of these newborn stars burn hot and bright, quickly exhausting their fuel and ending their lives in spectacular supernova explosions. Not all mergers end with one galaxy absorbing another. Some encounters are close enough to distort the galaxies involved, but not completely consume them. These interactions can stretch galaxies into strange shapes, creating long tidal tails or even bridges of stars that link two galaxies together. Some galaxies appear to have enormous loops of stars extending far beyond their central regions, likely the result of past interactions. Others have been left as deformed, chaotic structures, their spiral arms twisted beyond recognition. One of the most famous examples of galactic interaction is the antennae galaxies. Located about 60 million light-years away, this pair of colliding galaxies is caught in the process of merging. Their once distinct shapes have been shattered by gravitational forces, leaving behind two tangled structures connected by long, sweeping tails of stars and gas. Within these chaotic regions, new stars are forming at an incredible rate, making the antennae galaxies one of the most active star-forming regions we can observe. As galaxies consume one another, they grow larger and more complex. But there is a limit to this process. In the distant future, the expansion of the universe will continue to pull galaxies apart. The local group, currently held together by gravity, will eventually become an isolated island in an ever-darkening universe. Over time, as galactic mergers play out and the last of the smaller galaxies are consumed, only a few massive galaxies will remain. Their interactions will become rarer, and star formation will slow as gas supplies are used up. The hissing relics of the Big Bang, cosmic microwave background anomalies. The universe carries echoes of its own birth, a faint but persistent glow that fills all of space. This is the cosmic microwave background, the oldest light in existence, stretched and cooled over billions of years. It is a relic of the Big Bang, a remnant of the time when the universe was young, hot, and dense. Today, it appears as a uniform, low-energy radiation spread across the sky, detected by radio telescopes in all directions. But beneath this apparent smoothness, subtle patterns and strange anomalies have been found, irregularities that continue to puzzle scientists and challenge our understanding of the cosmos. The cosmic microwave background, or CMB, was first detected in 1964 by Arno Penzias and Robert Wilson, two radio astronomers who initially mistook it for interference. It turned out to be the oldest light in the universe, dating back to a time when the cosmos was only 380,000 years old. Before that moment, the universe was so hot and dense that light could not travel freely. Instead, it was scattered by electrons, trapped in a thick fog of plasma. As the universe expanded and cooled, electrons and protons combined to form the first neutral atoms. Light was finally able to escape, spreading out in all directions, carrying with it a snapshot of the universe as it was at that time. Over the past several decades, increasingly sensitive instruments have mapped the CMB in extraordinary detail. NASA's COBE satellite in the 1990s provided the first precise measurements, confirming that the CMB was nearly uniform, with only tiny fluctuations in temperature. These fluctuations were crucial as they represented the earliest seeds of structure in the universe, the slight variations in density that would later grow into galaxies, clusters, and voids. Later, the Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite refined these measurements, revealing even more intricate details in the cosmic background radiation. Despite its overall uniformity, some regions of the CMB appear slightly warmer or cooler than expected. These temperature variations are measured in fractions of a degree, but they hold important clues about the early universe. Most of these fluctuations align well with what is predicted by the Standard Model of Cosmology, which describes how the universe evolved from the Big Bang to the present day. But some anomalies refuse to fit within this framework. One such anomaly is the so-called cold spot, a vast region of the sky where the CMB is unusually cool. Located in the constellation Eridanus, this area is colder than its surroundings, and its presence has been difficult to explain. Some theories suggest that the cold spot is the result of a supervoid, a massive empty region of space that affects the light travelling through it. As the CMB photons pass through the void, they lose energy in a process known as the integrated Sachs-Wolf effect, which could account for the lower temperature observed in this part of the sky. Another unexplained feature in the CMB is the hemispherical asymmetry, an observation that one half of the sky appears slightly different from the other. According to the Standard Model of Cosmology, the CMB should look statistically the same in all directions. Yet when astronomers analyze the data, they find that one hemisphere of the universe has slightly stronger temperature fluctuations than the other. This imbalance is subtle but persistent, and it raises questions about whether something unexpected occurred in the early universe, perhaps a large-scale physical process that left an imprint on the CMB. Even more puzzling is the axis of evil, a term given to a strange alignment of temperature fluctuations in the CMB. When scientists map out the larger scale patterns in the microwave background, they find that certain features appear to be oriented along a specific axis, rather than being randomly distributed as expected. This alignment has led some researchers to wonder if our understanding of the universe's large-scale structure is incomplete. Some think that it could be evidence of a hidden force, a relic of physics beyond the Big Bang model, or even a sign that the observable universe is part of a larger, more complex reality. Cosmic inflation, the brief exponential expansion of the universe in the moments after the Big Bang, offers one possible explanation. If inflation was not perfectly uniform, it could have left behind subtle imprints in the CMB, creating the asymmetries and temperature fluctuations seen today. But some researchers have proposed that our universe may have collided with another universe in the distant past, leaving behind scars in the CMB. Beyond the large-scale anomalies, there are also unexplained signals hidden within the fine structure. Some studies have suggested the presence of non-random patterns that cannot be fully accounted for by known physics. These could hint at unknown particles or forces that influence the universe in its earliest moments. Some propose that hints of dark matter or dark energy might be buried in these temperature variations, waiting to be uncovered by more advanced observations. The recently constructed Simons Observatory will provide higher resolution maps of the CMB, potentially revealing new details about these anomalies. If a clear explanation is found, It could confirm or refine our current theories about the origin and evolution of the universe. But if the anomalies persist, they may point toward new physics, something beyond our current understanding of space and time. For now, the cosmic microwave background remains a whisper from the past, carrying with it the secrets of the universe's first moments. The cold embrace of the cosmic graveyard, derelict space probes. The earliest space probes, launched in the mid-20th century, were simple in design, but carried the weight of humanity's first steps beyond Earth. Some never made it past their launch stages, while others fulfilled their missions before slipping into a state of permanent dormancy. The first generation of probes, like the Soviet Lunar series and the American Pioneer missions, were crude by modern standards, but they were among the first mechanical explorers of space. Over time, these efforts evolved into more sophisticated interplanetary travelers, designed to visit the Moon, the planets, and eventually venture beyond the solar system. Some of these spacecraft were not meant to last. Many lunar landers, for instance, were designed for a single use, crashing into the surface after completing their primary objectives. The impact sites of these landers still exist on the Moon, untouched by erosion, their remains scattered across the dusty terrain. The Surveyor landers, early robotic explorers of the Moon in the 1960s, are still where they fell silent, their metal bodies slowly deteriorating in the unfiltered radiation of space. The Apollo lunar modules, abandoned after their astronauts returned home, remain standing as testaments to human presence in an otherwise lifeless landscape. Further from Earth, probes that once transmitted images of distant planets have now gone silent, their signals lost forever. The twin Voyager spacecraft, launched in 1977, are still operational, but their power supplies are dwindling. Eventually, they too will join the ranks of dead probes, drifting endlessly through interstellar space. They are among the few human-made objects that have escaped the solar system, travelling toward the unknown. Even when they go silent, they will continue moving untouched by time, perhaps forever. Some probes, like the Galileo spacecraft, met their ends in fiery descents. Galileo, which studied Jupiter and its moons, was deliberately sent plunging into the gas giant to prevent any risk of contaminating Europa, a moon that could potentially harbour life. Similarly, the Cassini spacecraft, after spending years orbiting Saturn, was directed into the planet's atmosphere, where it burned up. Other probes have become marooned in deep space, cut off from Earth by failed systems or power loss. Pioneer 10 and 11, once heralded as the first spacecraft to reach the outer solar system, are now beyond contact, drifting silently through interstellar space. Their trajectories will carry them through the galaxy long after the civilizations that built them have vanished. No one knows if they will ever be found again, if they will someday be intercepted by another intelligence, or if they will simply continue their solitary journeys for eternity. Closer to home, numerous satellites and probes have become part of the growing graveyard of artificial objects in orbit around Earth. Old communication satellites, defunct weather stations, and experimental spacecraft form a ring of technological debris encircling the planet. Some of these objects will eventually burn up in Earth's atmosphere, while others will remain in orbit for centuries. The Vanguard 1 satellite, launched in 1958, still circles the Earth, long inactive but still marking its presence among the stars. Mars too has become a final resting place for many robotic explorers. The surface of the red planet is scattered with the remains of landers and rovers that have outlived their missions. The Spirit rover, which once roamed the Martian terrain, became stuck in soft soil in 2009. Engineers fought to revive it for months, but it eventually went silent, abandoned where it stood. Its twin, Opportunity, lasted an astonishing 15 years before finally succumbing to a dust storm that cut off its solar power. Their tracks remain imprinted in the dust, slowly fading under the red sun. There is a strange irony in these abandoned machines. They were built with precision, equipped with instruments that could reveal the secrets of the universe, yet in the end, they are left to drift or decay. The very forces they were sent to study, the gravity of planets, the radiation of distant suns, now shape their fates. Without guidance from Earth, they are at the mercy of the cosmos. But even in their silence, these derelict probes hold meaning. They are markers of humanity's journey into space, evidence that, for a brief moment, Earth reached beyond its own atmosphere and sent explorers into the unknown. Some will remain visible to telescopes, while others will fade into darkness. Their legacy is not in their continued existence, but in what they have already accomplished. The images they sent back changed our understanding of the solar system. Their measurements helped shape our knowledge of distant planets and moons. Even those that failed on their journeys served as stepping stones, lessons for future missions. In time, humanity may return to the places where these probes were left. Future explorers might one day find the silent remains of spirit on Mars, or stumble upon the shattered remains of early lunar landers. The voyagers may drift for millions of years before encountering something, or nothing at all. But no matter their fate, these derelict probes remain as silent sentinels of human ambition. The cosmic hive mind. Is the universe a single conscious entity? If consciousness is not unique to living beings, if it can somehow emerge on a cosmic scale, then the universe might be more than just a collection of stars, galaxies, and black holes. It might be thinking, it might be aware. Some scientists and philosophers have explored this idea through the lens of panpsychism, a theory suggesting that consciousness is a fundamental property of reality, present even in the smallest particles. If true, then the building blocks of the universe, protons, electrons, quarks, might not just be passive components of matter, but tiny pieces of awareness. This doesn't mean that an atom thinks in the way a human does, but it raises the possibility that, when organized in a particular way, consciousness could emerge on a much larger scale. The brain is made up of billions of neurons, each individually insignificant, but when connected, forming something capable of thought, memory, and perception. Some people have wondered whether galaxies could function in a similar way. Massive structures of matter and energy linked by the cosmic web of dark matter and gravity. If a brain requires a network of connections to process information, the universe already has something similar. Vast filaments of galaxies stretching across space, resembling the neural pathways inside a mind. Simulations of cosmic structure show patterns that look strikingly similar to neural networks. Both systems operate under fundamental principles of connectivity, with clustered nodes linked by pathways. In the universe, those nodes are galaxies. In the brain, they are neurons. The patterns of growth, interaction, and even information transfer appear eerily alike, leading some to question whether the universe could function as a vast, self-organizing intelligence. If the universe is conscious, then what does it think about? Some have suggested that it may not think in any way humans can comprehend, just as a single neuron in a person's brain has no awareness of the thoughts that emerge from billions of interconnected neurons. The universe may be processing something so vast and complex that human minds are incapable of grasping it. If intelligence emerges naturally from connected systems, then it is possible that the universe as a whole is the largest and most advanced intelligence of all, one that has existed since the beginning of time. On Earth, intelligence did not appear all at once. It emerged gradually, shaped by time, adaptation, and experience. If the universe functions like a mind, then is it in its infancy, still developing awareness? Or has it existed long enough to reach a level of thought beyond anything humans can conceive? If galaxies, stars, and planets are part of its thinking process, then civilizations might act as neurons firing within a larger system, each one contributing in some small way to the universe's overall awareness. Some interpretations of quantum mechanics suggest that reality does not truly exist in a fixed state until it is observed. If observation creates reality, then what was happening before the first conscious life emerged? Some have suggested that the universe itself must be observing itself, meaning that consciousness, on some level, has existed since the very beginning. This would mean that the universe is not just a collection of lifeless matter, but something actively participating in its own existence. Some researchers have even speculated that what humans perceive as random cosmic events, such as quantum fluctuations, galaxy formations, or even the birth of stars, could be part of an unseen process of universal cognition. A more radical idea is the concept of the self-simulating universe. This theory suggests that reality itself is generated by its own consciousness, a feedback loop in which the act of existing and the act of perceiving existence are one and the same. In this case, everything from the motion of galaxies to the thoughts of individuals might be different aspects of a single, all-encompassing intelligence. Of course, none of this is proven. The idea that the universe could be a conscious entity remains in the realm of speculation and philosophy, rather than established science. There is no direct evidence that galaxies think, or that the universe is aware of itself. But the patterns found in cosmic structures, the strange properties of quantum mechanics, and the nature of consciousness itself all hint at possibilities that challenge human understanding. The void that shouldn't exist. The Boötes void's unexplained emptiness. Spanning approximately 330 million light-years across, the Boötes void is among the largest known voids in the universe. If the universe were a city, full of towering skyscrapers of galaxies, this would be a vast, empty lot stretching beyond the horizon. Given its size, one might expect thousands of galaxies to populate this space, yet astronomers have only identified a few dozen. It is not merely a region with fewer galaxies than expected. It is an anomaly, a vast desert in an otherwise bustling metropolis of stars. When astronomers first discovered the Boötes void in the 1980s, its sheer emptiness defied expectations. The universe follows a pattern, with galaxies clustering together in long filaments and forming massive superclusters, all connected like a web stretching through the cosmos. Between these clusters, voids naturally exist, regions with fewer galaxies than average. But the Boötes void is extreme, far larger and emptier than models predicted. Theories have emerged, each attempting to unravel the mystery of how such an empty space could form. One possibility is that the void was once populated by galaxies, but over time they were drawn away by the gravitational pull of denser regions nearby. In this scenario, the void did not begin as empty, but was gradually hollowed out by the slow tug of surrounding galactic clusters. Another idea suggests that the void is a relic of the early universe, a place where the density of matter was lower than usual right after the Big Bang. As the universe expanded and galaxies formed, regions with less matter naturally remained underpopulated. If this is true, then the Boötes void is a kind of cosmic fossil, a window into the past, revealing the uneven distribution of matter in the universe's earliest moments. Some astronomers speculate that the void might not be empty in the way it seems. It is possible that faint, dim galaxies exist within it, hidden from our view. Many galaxies, especially older ones, contain little star formation and produce only weak light, making them difficult to detect. If such galaxies exist within the Boötes void, they could explain why it appears so barren while still containing some matter. However, even if this were the case, it would still be one of the most underpopulated regions in the known universe. The scale of the Boötes void is difficult to grasp. If the Milky Way were inside it, the nearest galaxies would be so distant that humanity might never have discovered them. In a cosmic sense, it would be an almost perfect isolation. No neighboring galaxies to interact with, no nearby clusters to influence its shape or structure. Any civilization within such a void would face an extraordinary challenge, as the usual markers of cosmic geography, the light of nearby galaxies, the gravitational effects of massive clusters, would be nearly absent. The night sky, even in its most brilliant clarity, would be unnervingly empty. Despite its eerie emptiness, the Boötes void is not entirely devoid of galaxies. A small number, just a few dozen, are scattered throughout, defying the overwhelming isolation around them. These galaxies are like islands in an ocean, lonely and disconnected from the larger structures of the universe. Their very existence raises questions. How did they form in such a barren space? Were they once part of a larger structure, only to be left behind? Voids are not just empty spaces, they influence the way matter moves and interacts. Galaxies on the edges of voids experience different gravitational forces than those in denser regions, affecting their motion over billions of years. The existence of such massive voids also challenges models of how matter was distributed after the Big Bang, forcing astronomers to refine their understanding of cosmic evolution. The Boötes void is not unique. Other voids exist throughout the cosmos, though few reach its immense size. The Eridanus supervoid, for example, has been linked to the unexplained cold spot in the CMB, suggesting that these empty regions may hold even deeper mysteries about the early universe. As our tech advances, astronomers continue to search for other voids, mapping the universe's structure with increasing precision. Each discovery adds another piece to the puzzle, revealing the vast and complex nature of the cosmos. The impossible stars that defy our understanding of stellar life. Stars follow a predictable life cycle, shaped by their mass and composition. They are born from collapsing clouds of gas, ignite through nuclear fusion, and live for millions or billions of years, before ending as white dwarfs, neutron stars, or black holes. This fundamental understanding of stellar evolution has been built over centuries of observation and theory. Yet there are some stars in the universe that seem to defy these rules, existing as anomalies that challenge what scientists believe about how stars should behave. One such enigma is a star known as Methuselah, or HD 140283. Located about 200 light-years away, it appears to be older than the universe itself. Some measurements suggest that Methuselah could be as much as 14.46 billion years old, while the estimated age of the universe is about 13.8 billion years. This paradox should be impossible. No star can predate the Big Bang. But Methuselah's age, based on its metal content and brightness, suggests otherwise. Some astronomers believe that uncertainties in its age calculation could resolve the contradiction, but even the most conservative estimates place it uncomfortably close to the age of the universe. It remains one of the most baffling stellar objects ever observed. Then there are the stars that burn far too brightly for their supposed age. Some of the oldest known stars appear to be far too massive and energetic given their estimated lifetimes. In theory, large stars burn through their nuclear fuel quickly and should not survive for billions of years. Yet astronomers have detected ancient stars that seem to contradict this expectation. These stars should have either collapsed into black holes or gone supernova long ago, yet they persist, as if frozen in time. Some stars also seem to have compositions that do not match their place in the universe. The first stars, known as population 3 stars, are believed to have been made almost entirely of hydrogen and helium, the simplest elements formed after the Big Bang. These ancient stars should no longer exist, as they would have burned out billions of years ago. Yet astronomers have found stars with almost no heavy elements, resembling the very first stars in the universe, despite existing in regions where much younger stars dominate. These objects raise the question of whether truly ancient stars can survive far longer than previously thought, or whether unknown processes allow such stars to persist in unexpected ways. KIC 8462852, often called Tabby's star, displays dramatic and unpredictable dips in its brightness, unlike anything seen before. Most stars with changing brightness do so in regular, predictable cycles, either due to orbiting planets or changes in their outer layers. But Tabby's star dims in ways that do not fit any known pattern. Some scientists have suggested that an enormous cloud of dust surrounds the star, while others have speculated about more exotic explanations, such as a swarm of comets or even artificial megastructures. So far, no theory fully explains its strange and erratic behaviour. There are also stars that should have been destroyed long ago, but continue to exist. Some white dwarfs appear to be burning hotter than they should, as if they are being reignited by an unknown mechanism. Even neutron stars, which are typically well understood, occasionally break the rules. These dense remnants of supernova explosions usually spin rapidly and emit predictable pulses of radiation. However, a few neutron stars behave unpredictably, with irregular slowdowns and speed-ups in their rotation. Some suddenly brighten with bursts of energy that should not be possible given their structure. These erratic behaviours hint at unknown physical processes taking place deep within these stars, processes that might involve exotic states of matter or even unknown forms of quantum interactions. Some stars have been found floating alone in intergalactic space, far from any galaxy. In theory, these stars may have been ejected from their home galaxies by gravitational interactions, but their existence raises questions about how often such events occur and whether there are entire populations of orphan stars drifting unseen in the void between galaxies. Even within our own Milky Way, there are stars that challenge expectations. Some appear to have gathered heavy elements from unknown sources, showing chemical compositions that do not match the environments in which they are found. Each of these impossible stars represents a challenge to the established models of stellar evolution, hinting at fundamental processes that remain undiscovered. Whether through new physics, unknown stellar interactions, or simply measurement errors waiting to be corrected, these stars are cosmic puzzles begging to be answered. Temporal echoes, when time bends in the void. One of the strangest ideas in modern physics is that time is not an absolute force, but something that can be influenced by gravity. The stronger the gravitational pull, the slower time moves. This effect, known as time dilation, has been confirmed through experiments here on Earth. A clock placed at the top of a mountain will tick slightly faster than a clock at sea level, where Earth's gravity is stronger. But in space, where gravity can reach unimaginable extremes, time itself begins to behave in ways that defy common sense. Near a black hole, time slows dramatically. If an observer were to watch a spacecraft approaching the event horizon, it would appear to move slower and slower, until at the very edge, it would seem frozen in place. But for the astronaut on board, time would feel normal. They would continue moving forward until they crossed the threshold, disappearing from the universe's view. This effect is not just a thought experiment, it is something that must be considered when dealing with objects near extreme gravitational forces, such as neutron stars or supermassive black holes. The closer something gets to these cosmic monsters, the more time stretches, making a single second for one observer feel like years to another. There are places in the universe where time may not only slow, but fracture, creating strange echoes of the past. Some scientists speculate that in regions with intense gravitational distortions, light from past events could become trapped, creating the illusion of history playing on an endless loop. If a planet were orbiting near the right kind of gravitational anomaly, An observer might see the same supernova explosion repeat over and over, the event forever suspended in time. There is even speculation that some of the unexplained radio signals detected from deep space could be echoes of past transmission, bent and redirected by the warping of space-time. Even more unsettling is that theoretical physics suggests that the fundamental laws of the universe do not necessarily require time to move in only one direction. In some models, particles behave exactly the same, whether time is moving forward or backward. While this is not something we see in our daily lives, there are scenarios where extreme physics might allow time to run in reverse. One idea is that inside a black hole, beyond the event horizon, space and time switch roles. What was once forward movement through time might become forward movement through space, trapping anything inside in a region where time itself no longer behaves in a way we can understand. There are also theories that suggest entire pockets of the universe could be moving through time in a different direction. If our universe is part of a larger multiverse, it is possible that other regions experience time backward from our perspective. If someone from such a place were to look at us, they would see our universe as rewinding, just as we might see theirs doing the same. Ideas such as these raise profound questions about the true nature of time and whether it is as linear as we believe. Just as ancient fossils provide a record of Earth's history, some scientists believe that the fabric of space-time could retain imprints of previous cosmic events. Certain anomalies in the CMB have led some researchers to speculate that we may be seeing traces of previous universes, or even echoes of cosmic structures that no longer exist. Time behaves differently depending on where you are in the universe, but what if it could also behave differently depending on when you are? The concept of time loops, where an event repeats endlessly, is a common theme in fiction, but some physicists take the idea seriously in the context of closed time-like curves. These hypothetical paths through space-time could allow for scenarios where an event causes itself, where the future influences the past in a way that defies traditional logic. Some solutions to Einstein's equation suggest that under the right conditions, space-time could fold in on itself, creating a loop that allows something or someone to experience the same moment indefinitely. As the universe continues expanding, some scientists predict that the stretching of space-time will eventually slow all motion to the point where change itself ceases. In such a scenario, time would still technically exist, but there would be no events to mark its passage. It would be as if the universe itself had frozen, a silent monument to everything that had ever been. Unlike space, which we can move through freely, time seems to move in only one direction, pulling everything forward at the same constant rate, at least as far as we can tell. But the deeper we explore the universe, the more we find exceptions to this rule. Time bends, it slows, it stretches, and perhaps in the strangest corners of the cosmos, it even turns back on itself. The zombie stars that keep coming back to life. When a star reaches the end of its life, it is expected to either fade into obscurity or explode in a violent death. But in rare cases, some stars refuse to follow the script. These are the so-called zombie stars, remnants that should be long gone, but instead show signs of renewed activity. One type of zombie star is a white dwarf that seems to reignite itself. White dwarfs are the burned-out cores of once luminous stars like the Sun, left behind after the outer layers have been shed into space. Without a source of nuclear fusion, they are supposed to cool and fade over billions of years. Yet some white dwarfs have been found behaving as if they are still active. These stars experience unexpected bursts of brightness, emitting radiation that suggests nuclear reactions might still be occurring on their surfaces. One explanation is that these white dwarfs are stealing material from a companion star, collecting gas onto their surface until it ignites in a sudden thermonuclear explosion. These outbursts, known as nova events, can cause the star to briefly shine as brightly as 1 million suns, before fading again. If a white dwarf gathers too much material from its companion, it can cross a critical mass threshold and undergo a much larger explosion, a type 1, a supernova. These events were once thought to be the final destruction of the star, leaving nothing behind. But in some cases, astronomers have detected remnants of the white dwarf after the explosion, still glowing faintly as if part of it had survived. This suggests that instead of being completely obliterated, some white dwarfs endure these cataclysmic events and continue to exist, even after what should have been their final death. In at least one case, astronomers have observed a star that exploded and then appeared to be intact afterward. The star, known as IPTF 14HLS, was first thought to be a typical supernova when it was detected in 2014. But instead of fading over the following months as expected, it continued shining for years, experiencing multiple peaks in brightness. This was completely unexpected. Supernovae are supposed to be one-time events, with the star collapsing or being blown apart. Yet this star refused to disappear. The leading theory is that IPTF14HLS may be a type of star that undergoes repeated eruptions, losing mass in violent outbursts rather than being completely destroyed in a single explosion. If true, it could represent a rare class of stars that do not die in the usual way, instead experiencing a long and drawn-out process of repeated near-deaths. Some stars seem to flicker back to life after disappearing for long periods. These objects, sometimes called vanishing stars, are cases where astronomers observe a star in one set of images, only for it to be completely gone in later observations. In a few rare instances, the star has later reappeared, seemingly unchanged. One possible explanation is that these stars experience extreme dimming events, where their light is temporarily blocked by dust clouds or other material. Another idea is that some stars may undergo a period of dormancy, where nuclear fusion slows down or stops for a time before restarting. If this is the case, it would suggest that stars may not be as permanent in their life cycles as previously thought. Even black holes, which represent the ultimate fate of the most massive stars, have shown hints of unexpected activity. In some cases, astronomers have observed bright flashes of radiation from regions where no active black hole was thought to exist. One possibility is that these signals come from black holes that had been inactive for millions of years, suddenly feeding on new material and producing bursts of energy. Some theories suggest that certain black holes might even experience cycles of activity, where they go dormant and then flare back to life under the right conditions. All of these strange objects suggest that death may not always be permanent in the cosmos. Instead, they remind us that the universe is full of surprises, where even the dead can sometimes return. Spaghettification. What happens when you fall into a black hole? Gravity is stronger the closer you get to a massive object, but in normal conditions, like standing on Earth, the difference between the pull of gravity at your feet and at your head is negligible. Near a black hole, however, the difference can be extreme. If someone were to fall in feet first, the gravitational pull at their feet would become significantly stronger than at their head. This difference in force, called a tidal force, begins to stretch the body in one direction while compressing it from the sides. At first, this effect might not seem too dramatic, especially far from the black hole. If someone were approaching a supermassive black hole, like the kind found at the center of a galaxy, their descent could seem almost ordinary at first. The gravitational gradient near the event horizon of a supermassive black hole is relatively shallow compared to a smaller stellar mass black hole, meaning the pull increases gradually. But as they continue falling inward, the forces become exponentially more extreme. For a person, this would first manifest as an intense sensation of being pulled downward. If they attempted to move their arms or legs, they would find it increasingly difficult. as the stretching force pulls everything toward a single point. Bones, muscles, and organs would feel like they were being stretched in ways never meant to happen. While the body is being pulled apart lengthwise, it is also being squeezed sideways. Imagine a lump of dough being rolled into a long, thin string. The closer they get to the event horizon, the more severe this stretching becomes. The effect is so powerful that it overrides the natural forces that hold matter together. At a certain point, the molecular bonds keeping a person's body intact can no longer withstand the difference in gravitational pull. The body would begin to break apart, first separating at the joints, then tearing into individual molecules, then atoms. A small black hole makes this process even more violent. If someone fell into a stellar mass black hole only a few times the mass of the Sun, spaghettification would begin much farther away from the event horizon. The gravitational pull increases so steeply that a falling object would be torn apart well before it ever reaches the black hole's boundary. This means that for most practical purposes, a person would never even reach the event horizon intact. This extreme process doesn't just apply to humans. Anything falling into a black hole undergoes spaghettification, whether it's a spaceship, an asteroid, or even an entire star. When a star drifts too close to a supermassive black hole, it is subjected to these same forces, though on a much larger scale. The black hole's gravity first pulls away the star's outer layers, stretching it into an elongated shape before completely tearing it apart. The remnants spiral into the black hole, forming an accretion disk. These tidal disruption events are among the most violent and luminous displays in the universe, producing bursts of X-rays and radiation detectable across vast distances. For an observer watching from a safe distance, the process would appear even stranger. Due to the effects of time dilation, where strong gravity slows the passage of time, anything falling into a black hole appears to slow down as it approaches the event horizon. If a person were falling in, an outside observer would see them gradually stretching out and dimming, their movement slowing to an almost imperceptible crawl. Eventually, they would appear frozen at the edge of the event horizon, never fully crossing over. But this is an illusion. From the perspective of the falling person, they would pass through the event horizon normally, without any sign that they had reached a point of no return. Beyond the event horizon, all paths lead toward the singularity, the infinitely dense core at the black hole's center. No known laws of physics describe what happens inside this region, but if spaghettification has not already reduced a falling object to subatomic particles, it will be completed here. Everything collapses into the singularity, where space and time cease to function in any recognizable way. The idea of being stretched into a thin, thread-like strand may sound purely theoretical, but it is a direct result of the equations of Einstein's general relativity. The warping of space near a black hole creates tidal forces so powerful that they overcome all other known physical forces. Unlike being crushed under immense pressure, which is how objects are destroyed in other extreme environments like neutron stars, spaghettification involves stretching to the point where matter is broken down into its most fundamental components. Despite its terrifying implications, spaghettification is one of the few black hole effects that scientists can study indirectly. By observing tidal disruption events, astronomers can measure the light and energy released as stars are pulled apart. This provides valuable insight into how black holes interact with their surroundings. The more we study these events, the more we learn about how black holes grow and evolve. Although no human has ever experienced such a thing, it remains one of the most dramatic fates that could befall anything in space. A black hole's pull is absolute, and once something crosses the event horizon, there is no coming back. For anything that gets too close, the result is the same, an inevitable, unstoppable descent into the unknown. The bottomless pit of Ton 618, the most massive black hole ever discovered. Ton 618 is a cosmic monstrosity, one of the largest known black holes we have ever discovered. This black hole sits at the heart of a quasar more than 10 billion light-years away, a distant beacon of incredible power. Based on current measurements, Ton 618 has an estimated mass of 66 billion times that of the Sun. It is so massive that it defies many of the models used to explain how black holes grow over time. The numbers attached to Ton 618 are almost impossible to grasp. The event horizon is so large that it could swallow our entire solar system many times over. If this black hole replaced the Sun at the center of our solar system, its edge would extend well past the orbit of Pluto, and its gravity would dominate everything within thousands of light years. The accretion disk surrounding it shines so brightly that it outshines entire galaxies. It emits so much energy that it is classified as a quasar, one of the brightest objects in the universe. The formation of such a gigantic black hole is a mystery. Black holes grow by consuming gas, dust, stars, and even other black holes, but the process is not unlimited. When a black hole's accretion disk gets too hot, the radiation it emits pushes back against incoming material, slowing down its growth. This self-regulating process, known as the Eddington limit, should place a natural cap on how massive a black hole can become within a given time. Ton 618's size suggests that either it has been consuming matter at an extreme rate for billions of years, or that it formed through unknown mechanisms. One possibility is that Ton 618 began its life as a primordial black hole, forming in the earliest days of the universe when conditions were far different from today. Another theory suggests that it may have started as a small cluster of black holes merging together, eventually collapsing into a single, supermassive entity. However, even these explanations struggle to fully account for its staggering size. A black hole as massive as Ton 618 warps space and time in extreme ways. The gravitational influence of this black hole extends for thousands of light years, subtly shaping the motion of nearby galaxies. Light passing near it is bent and distorted, creating gravitational lensing effects that allow astronomers to study objects hidden behind it. In a sense, Ton 618 acts as a giant cosmic magnifying glass, altering the appearance of the universe around it. The quasar it powers is visible across billions of light years, meaning the light we observe today was emitted when the universe was only a few billion years old. This suggests that Ton 618 has been a dominant force for much of cosmic history, influencing the evolution of galaxies in its region of space. The powerful radiation pouring from its accretion disk prevents new stars from forming nearby, shaping the fate of entire systems. While it remains one of the largest known black holes, other ultramassive black holes may be lurking in the universe, hidden within the cores of distant galaxies. Some estimates suggest that black holes even larger than Ton 618 could exist, though they would be incredibly difficult to detect. Since black holes do not emit light themselves, they are only visible through the effects they have on their surroundings. A truly isolated black hole of similar mass without an active accretion disk would be nearly impossible to find. The more we study objects like this, the more we realize how much remains unknown about the deepest, darkest parts of the cosmos. The other side of the event horizon. Could something escape after falling in? A black hole's event horizon is often described as the ultimate point of no return. Anything that crosses it is lost to the black hole forever, pulled inevitably toward the singularity at the center. According to Einstein's theory of general relativity, no information can escape from inside the event horizon. The very fabric of space and time is so distorted by gravity that all possible paths lead inward. No force in the universe, not even the fastest particle or the most energetic explosion, can fight against the black hole's pull once that threshold is crossed. But is it truly the end? Or is there a possibility, however small, that something might escape after falling in? The idea seems impossible under classical physics, yet theories in quantum mechanics suggest that the event horizon may not be an absolute barrier. Some scientists believe that information might not be lost forever, but instead remains imprinted in ways we do not yet understand. One of the most famous challenges to the idea of a black hole as a perfect prison comes from Stephen Hawking's research on black hole radiation. In the 1970s, Hawking proposed that black holes are not completely black. Instead, they slowly emit what is now called Hawking radiation, a faint glow that results from quantum effects near the event horizon. This radiation causes black holes to lose mass over time, eventually evaporating entirely. But there is a problem. If a black hole vanishes, what happens to everything that fell into it? The laws of physics suggest that information should never be completely destroyed, yet black holes seem to do just that. Some scientists believe that information might be encoded in the radiation itself, subtly leaking out over time as the black hole shrinks. Others suggest that the information never really falls in, but instead remains on the surface of the event horizon, like a hologram storing data in 2 dimensions, while the 3-dimensional object it represents appears to be inside. This is known as the holographic principle, a radical idea suggesting that everything inside a black hole might actually exist as an imprint on its outer boundary. Another theory proposes that black holes might not be the one-way traps we assume them to be. Some physicists have suggested that under certain conditions, matter could escape through quantum tunneling, a process where particles can seemingly bypass barriers that should be impossible to cross. If such an effect occurs in black holes, it could mean that some fraction of the material swallowed by a black hole might, given enough time, make its way back out. Some theories push the speculation even further. In certain models of quantum gravity, black holes might connect to other parts of the universe, or even other universes, through theoretical structures known as wormholes. If true, then matter falling into a black hole might not be lost, but instead transported elsewhere through a cosmic shortcut. This idea has been explored in physics for decades, though no evidence of such a connection has been found. Some physicists speculate that the intense gravitational forces near the singularity might give rise to unknown physical conditions, creating exotic states of matter, or even generating new universes in a process similar to the Big Bang. In this view, the collapse of a star into a black hole may not be the end of its story, but the beginning of something else entirely. Perhaps even another universe that expands from the singularity like our own did billions of years ago. Yet despite these ideas, no observation has ever shown anything leaving an event horizon, and the mathematics of relativity still suggest that nothing can cross back once it has fallen in. Even if some of these theories turn out to be correct, the timescales involved may be so vast that any escape process would take longer than the lifespan of the universe itself. The paradox of black hole information loss continues to challenge physicists. Some believe that the true nature of black holes is still unknown, that our understanding of space, time, and gravity is incomplete. If we one day solve this mystery, it could change everything we know about the fundamental structure of the cosmos. Until then, black holes remain the most enigmatic objects in the universe, silent and all-consuming. Black dwarf supernovae, the last fireworks in a dying universe. For trillions upon trillions of years, the universe will darken. The last red dwarfs will flicker out, turning into cold, dead husks. Galaxies will dissolve as their stars die one by one. Black holes, once the dominant force in the cosmos, will gradually evaporate, losing their mass through an almost imperceptible trickle of Hawking radiation. The sky, once ablaze with the light of countless stars, will become an abyss of infinite blackness. But even in this silent, decaying universe, there may still be one final moment of light, a last cosmic explosion that will briefly pierce the darkness before everything fades away forever. A black dwarf supernova is an event that, if it happens, will be one of the last great acts of the universe. It is not something that can occur today or even in the next trillion years. Instead, it is a process so slow that it requires the death of time itself to set the stage. At the heart of this phenomenon are black dwarfs, a type of star that does not yet exist anywhere in the cosmos. Black dwarfs are the hypothetical remains of white dwarfs. Today, white dwarfs still glow faintly, radiating away the residual heat left over from their earlier lives. Over quadrillions of years, this heat will slowly vanish, leaving behind a frozen, inert object. Without energy, without fusion, and without light, a black dwarf will be a dead star in every sense of the word. It will be made of carbon and oxygen crushed into an ultra-dense state, far heavier than anything we can create on Earth. It will not shine, will not radiate heat, and will be nearly impossible to detect. If someone or something were to drift close enough, it would appear as little more than an invisible sphere of degenerate matter, a frozen corpse of a long extinguished sun. But these stars, for all their silence, may not be entirely lifeless. Under the right conditions, the very atoms within a black dwarf could trigger one last, explosive farewell. The key lies in a slow and inevitable process: quantum tunneling. In ordinary stars, fusion occurs due to immense heat and pressure, forcing atomic nuclei to slam into each other at high speeds. But in the frozen core of a black dwarf, there is no longer any fusion taking place. The star's carbon and oxygen atoms are locked in place, held together by the crushing weight of their own gravity. However, quantum mechanics allows for a strange and rare phenomenon: tunneling, where particles can pass through energy barriers that they would normally never overcome. Even in the stillness of a black dwarf, this process continues at an agonizingly slow rate. Over the course of an inconceivable amount of time, a handful of atomic nuclei will fuse. The effect will be so slight that it would take an eternity to build up any real impact. But time, in a dying universe, is the one thing that remains in limitless supply. After a staggering 10 to the power of 1500 years, a number so large it is almost meaningless, enough of these reactions will have taken place to trigger a runaway fusion event. The core of the black dwarf, now slowly converting its carbon into iron, will reach a breaking point. Just as in today's massive stars, the buildup of iron will create an unstoppable collapse. Gravity, no longer held at bay by the weak remnants of nuclear forces, will take over. The core will implode, triggering a massive explosion, a supernova, erupting with all the energy of a dying star, even though the universe itself has long since grown cold. For a brief moment, in a cosmos where no light has shone for untold epochs, a single star will blaze back to life. The explosion will send shockwaves through the empty void, though there will be nothing left to receive them. A cloud of gas and dust, remnants of the black dwarf, will scatter outward. But unlike the supernovae of earlier cosmic history, this one will leave nothing behind. No neutron star, no black hole, only the fading remnants of its own final light. If black dwarf supernovae do occur, they will be among the last sources of energy the universe will ever see. As they become rarer and rarer, there will come a time when the very last one detonates, unleashing the last supernova in all of history. And then, after that final burst, there will be nothing. No more reactions, no more explosions, no more light. The last remnants of the stars will be gone, and the universe will enter its final, silent darkness. Proton decay and the slow dismantling of matter. Even in the deep future, long after the last supernova has faded, after the last stars have cooled into lifeless husks, there will still be something left: matter itself. The atoms that make up the universe, the protons and neutrons that form the very structure of reality, are the last pieces of existence that will remain. But even these may not be eternal. If the theories predicting proton decay are correct, then the slow dismantling of matter is an unavoidable fate, one that will unfold on timescales so vast they make even the life of the longest-lived stars seem fleeting. Protons, the fundamental building blocks of atomic nuclei, are currently considered to be stable. Every atom in existence relies on their persistence. Without them, matter itself would disintegrate. But many grand unification theories, which seek to connect the fundamental forces of nature, predict that protons do not last forever. Instead, they should slowly, almost imperceptibly, break down over time. If this is true, then even the most enduring structures in the universe are only temporary. Given enough time, everything must decay. The idea of proton decay arises from the attempt to unify the strong nuclear force with the electroweak force, forming what physicists call a grand unified theory. The strong nuclear force is what holds atomic nuclei together, overpowering the repulsion between positively charged protons. If it were not for this force, atoms would fly apart in an instant. But if the strong force is not truly separate from the other fundamental forces, as many physicists suspect, then protons themselves must have a finite lifespan. The problem is that this lifespan, if it exists, is staggeringly long, far beyond the limits of any experiment that can be conducted within a human lifetime. If protons do decay, the process would be slow but inevitable. A single proton, left undisturbed, might last for at least 10 to the power of 34 years, more than 1 trillion times the current age of the universe. But on long enough timescales, one by one, they would begin to vanish. A proton, when it decays, does not leave behind any recognizable matter. Instead, it transforms into lighter subatomic particles, such as positrons and neutral pions, which quickly decay into gamma rays and neutrinos. Given enough time, all matter will dissolve into a thin, ghostly mist of radiation and near massless particles that drift endlessly through the void. The bonds holding together molecules will be meaningless if the protons within them cease to exist. Solid structures will dissolve, not into dust, but into pure energy, leaving no recognizable trace of what once existed. Black holes, the most enduring objects in the universe, may persist far longer than ordinary matter, but even they are not eternal. Due to Hawking radiation, black holes are expected to slowly evaporate over time, releasing faint trickles of energy into space. This process is extraordinarily slow, but inevitable. If proton decay occurs, then by the time the last black hole vanishes, all ordinary matter in the universe will have already been reduced to nothing. The final era of the universe, sometimes called the Dark Era, will be one of emptiness beyond comprehension. No galaxies, no stars, no planets, only an expanding void filled with stray photons, neutrinos, and the last whispering echoes of a universe that once was. Even the strongest structures, the most stubborn remnants of creation, will have vanished. In this vast and empty future, time itself will have lost meaning, for nothing will remain to measure its passage. The pale blue dot's fragile existence. Could Earth be forgotten? There is a photograph taken in 1990 by the Voyager 1 spacecraft. From nearly 6 billion kilometers away, it captures Earth as a single point of light, a fraction of a pixel against the vastness of space. This is the pale blue dot, as named by Carl Sagan, who reflected on its significance. Every person who has ever lived, every war fought, every joy, sorrow, and triumph has all unfolded on this tiny speck of light. And yet from that distance, Earth looks no different from a mote of dust floating in a sunbeam. From a cosmic perspective, our planet is fragile. Its existence depends on a delicate balance, just the right distance from the sun, an atmosphere just thick enough to sustain life, a magnetic field strong enough to shield it from harmful radiation. Even minor changes could turn Earth into a wasteland, incapable of supporting the billions of lives that depend on it. And despite all the achievements of human civilization, there is nothing protecting Earth from the vast, indifferent forces of the universe. Throughout history, the planet has endured catastrophes. Asteroid impacts have reshaped landscapes, mass extinctions have wiped out entire species, and climate shifts have threatened the balance of ecosystems. Each of these events reminds us of how easily our world could change, how quickly the conditions we take for granted could vanish. But these are just the immediate threats, the ones visible within the short timescale of human history. On longer timescales, Earth's position in the universe becomes even more precarious. Our Sun is not eternal. It was born about 4.6 billion years ago and will continue to burn for another 5 billion years. But long before it reaches the end of its life, the Sun will change. As it burns through its hydrogen fuel, it will grow hotter and more luminous. In as little as 1 billion years, Earth's surface may become uninhabitable, as rising temperatures cause oceans to evaporate and the atmosphere to break apart. Long before the Sun expands into a red giant, our world could already be lost. Even if life somehow endures on Earth for billions of years to come, the universe itself will not remain static. The continents will shift, reshaping coastlines beyond recognition. Supervolcanoes will erupt, altering climates in ways we cannot predict. New ice ages will come and go. At some point, the Moon, locked in an ever-slowing dance with our planet, will drift too far to stabilize Earth's tilt, leading to chaotic and unpredictable seasons. The Sun's growing heat will strip away what remains of the atmosphere, and Earth will become as barren as Venus or Mars. If humanity still exists by then, will anyone remember the Earth as it once was? Civilizations rise and fall in cycles, and time has a way of erasing even the grandest monuments. The pyramids of Egypt have endured for thousands of years, but given enough time, they too will crumble into dust. The cities of today, made of steel and glass, will collapse and be overtaken by the elements. If no intelligent life remains to preserve history, the evidence of human existence could disappear entirely. There may come a time when nothing is left of our world but a dead, frozen rock orbiting a dying sun. And as the Sun completes its transformation into a white dwarf, shedding its outer layers into space, even that final remnant of Earth could be obliterated. The very atoms that once formed mountains and oceans, that once made up every living creature, will be scattered across the void, unrecognizable. Even if some record of Earth survives, perhaps buried in a distant archive on another planet, or etched into a probe drifting between the stars, it will eventually be forgotten. If life does not spread beyond Earth, then everything that has ever been will one day vanish without a trace. And yet, despite this overwhelming impermanence, Earth matters. To the people who live on it, it is everything. It is home. It is the only place in the universe where life is known to exist. And for now, it is the only place where humanity can survive. Whether or not it will be remembered, whether or not it will be lost to time, the pale blue dot remains a world filled to the brim with meaning. The Forgotten Astronauts. Theories of lost cosmonauts in space. There are moments in history that remain uncertain, stories whispered but never confirmed, pieces of evidence that hint at something larger yet remain just out of reach. Among the many tales of early space exploration, few are as unsettling as those of the so-called lost cosmonauts, astronauts who may have vanished into the void, their names erased from official records, their fates unknown. The space race between the Soviet Union and the United States was marked by secrecy, ambition, and an urgent need for success. Every milestone was a victory, every failure a carefully buried secret. In this era of rapid technological advancements and intense political pressure, rumours emerged that not every attempt at spaceflight ended with a triumphant return. Some accounts suggested that cosmonauts had been launched into space, but never made it back. If true, These would have been the first humans to venture beyond Earth, only to be lost, unacknowledged, and forgotten. One of the earliest and most persistent claims of lost cosmonauts comes from a pair of Italian brothers, Achille and Giovanni Giudica Cordiglia. In the 1960s, these amateur radio operators in Italy claimed to have intercepted strange and distressing transmissions from Soviet spacecraft. Among these recordings was what they described as the faint, fading voice of a cosmonaut, reporting that their capsule was drifting away, lost in space. Another recording, they claimed, captured the final, desperate words of a cosmonaut trapped in a failing spacecraft, asking, "Isn't this dangerous?" before static consumed the signal. The Soviets never acknowledged any such missions. Their official records showed that the first human in space was Yuri Gagarin in April 1961, and every subsequent cosmonaut was accounted for. Yet some skeptics have pointed out inconsistencies in Soviet spaceflight reports, unexplained gaps in mission timelines, inconsistencies in crew announcements, and changes in official narratives that could suggest cover-ups. There were other strange incidents that fueled speculation. In 1959, an American journalist named Harrison Salisbury reported on a rumor from Soviet sources that a cosmonaut had died on a failed space mission. In 1960, an official Soviet statement declared that an astronaut named Valentin Bondarenko had died in a ground-based training accident, but some believed his name had initially been erased from records to avoid embarrassing the Soviet space program. Others pointed to photos of early cosmonaut training groups where certain individuals seemed to disappear from later pictures, raising suspicions that they had been part of secret, ill-fated missions. Of course, there are alternative explanations for these inconsistencies. The Soviet Union was known to be highly secretive about its space program, often withholding failures from public knowledge to maintain the image of success. If test pilots or engineers had perished during training or in uncrewed test launches, their names might have been removed from records, not as part of a sinister cover-up, but simply to keep failures from tarnishing the nation's achievements. Despite the lack of concrete evidence, the thought of a human being alone in the vast emptiness of space, doomed to drift until their oxygen runs out or their ship is claimed by the endless void, is a deeply unsettling one. If such a fate had befallen someone, there would be no grave, no marker, no way for loved ones to know where they had gone. The only evidence of their journey would be the cold metal shell of their spacecraft, tumbling silently through the cosmos, forever unclaimed. The legends of lost cosmonauts speak to something deeply human: the fear of being forgotten, the dread of isolation, the tragedy of disappearing without a trace. Even if these stories are nothing more than myths, they serve as a reminder of the risks taken by the pioneers of space exploration. Each launch carried the possibility of disaster. Each mission was a step into the unknown. Whether any cosmonauts were truly lost to space may never be known, but the idea lingers, a ghost story from the dawn of the space age, whispered in the static of the universe. Celestial time capsules, relics of forgotten civilizations. For billions of years, stars have formed, burned brightly, and died, scattering their remnants across space. Planets have emerged from swirling clouds of dust, some lifeless, others perhaps teeming with civilizations that have long since vanished. If intelligent life has arisen more than once in the cosmos, then it is possible that somewhere, hidden among the stars, are relics of those who came before. Silent, forgotten artifacts drifting through time. On Earth, archaeologists uncover ruins, tools, and writings from cultures that disappeared thousands of years ago. But on a cosmic scale, 1,000 years is nothing. If a civilization arose 1 billion years before us, what kind of evidence could possibly survive? Would it be something tangible, like a structure floating in interstellar space? Or something more subtle, encoded into the very laws of the universe? Some scientists have suggested that space itself could be a kind of museum, holding remnants of intelligent life in ways we have yet to recognize. One possibility is the existence of Bracewell probes, named after scientist Ronald Bracewell, who theorized that advanced civilizations might send self-replicating machines into space to act as beacons or messengers. Unlike radio signals, which fade over distance and time, these machines could persist, waiting in the darkness for someone to find them. If such probes exist, they might be hidden in the asteroid belts of planetary systems, orbiting long-dead stars, or even drifting unnoticed in the void between galaxies. The search for extraterrestrial intelligence has largely focused on listening for radio signals, but radio waves are fragile, subject to interference and decay. If a civilization wanted to send a message that would last for millions or even billions of years, they might have chosen a different method, one woven into the very structure of space. Some theorists have proposed that encoded messages could be hidden in the cosmic microwave background. Others have speculated that patterns in pulsar emissions or the arrangement of certain galaxies might be intentional, designed to be noticed by those capable of recognizing them. A more dramatic possibility is the existence of true megastructures. The concept of Dyson spheres, massive artificial shells built around stars to capture their energy, has been a popular idea for decades. If such structures exist, they would likely leave detectable signatures, such as unusual dips in a star's brightness or infrared radiation from excess heat. So far, no confirmed megastructure has been found, but the possibility of an ancient, abandoned megastructure still lingers. Other cosmic relics might take the form of modified celestial bodies. If an advanced civilization had the power to reshape planets, moons, or even entire star systems, the evidence of their work might still exist. Rogue planets, worlds drifting through space without a parent star, might not all be natural. Could some have been engineered, turned into self-sustaining arcs carrying life through the galaxy? If so, how would we recognize them? Even black holes have been considered as potential time capsules. If a civilization knew its time was coming to an end, could it have used black holes as a means of preserving knowledge? Could the radiation we detect from distant black holes contain something more than just the echoes of dying stars, an intentional, hidden message waiting to be decoded? There is also the possibility that the most enduring relics of an advanced civilization would not be material at all, but rather an influence on the evolution of life itself. If a civilization existed billions of years ago and found a way to seed the galaxy with life, their legacy might be hidden within the genetic code of every living thing. Some researchers have even considered the idea that DNA could carry messages, long sequences of genetic information that serve no known biological function, but might have been placed there intentionally. If such cosmic relics exist, finding them would be no small task. The universe is vast, and most of its history is unknown to us. But just as archaeologists on Earth carefully search for traces of ancient civilizations beneath layers of rock and soil, astronomers and physicists continue to search the cosmos for evidence that we are not the first to look up at the stars and wonder. Mirror worlds, dark twin universes. What if our universe was not alone, but instead had a shadow counterpart, a mirror world that exists alongside ours but remains invisible to us? The idea of a mirrored reality stems from serious scientific questions about the nature of symmetry in the universe, the properties of dark matter, and the fundamental laws of physics. In particle physics, there is an observed balance in how particles behave, known as charge parity symmetry. However, there are exceptions. Certain subatomic interactions violate this symmetry, leaving scientists wondering whether an undiscovered force or hidden realm might restore the balance. A mirror universe composed of particles that are reversed in certain fundamental properties could provide the missing piece to this cosmic puzzle. If such a universe exists, it would not be a simple copy of ours. It could be an eerie reflection, where the familiar rules of physics apply, but in an altered way. Some theories suggest that dark matter might be made up of particles from this hidden world. If mirror matter exists, it would interact with regular matter only through gravity, making it effectively invisible. This could explain why dark matter does not emit or absorb light, yet holds galaxies together. A truly mirrored universe might be connected to our own by more than just theoretical symmetry. Occasional interactions could take place between the two realms. If so, these interactions might appear as strange, unexplained phenomena in our own world. There are even experiments designed to look for evidence of particles disappearing from our universe and reappearing in a mirror universe, or vice versa. Some models propose that the Big Bang may have created not one universe, but two, one moving forward in time as we perceive it, and another moving in reverse. In this mirrored reality, time would flow in the opposite direction from our perspective. Inhabitants of such a universe would not experience time moving backward from their own viewpoint, just as we do not feel time flowing in any unnatural way. To them, we would be the ones seemingly running in reverse. If the fundamental forces of nature are slightly different in a mirror world, then chemistry could behave in unusual ways. Stars might burn at different rates, and planets might form under entirely different conditions. A mirror version of Earth, if it existed, might not be recognizable. Life, if present, could be structured in ways that defy our understanding of biology. It is even possible that the rules governing intelligence and consciousness could be different, leading to minds that operate in ways beyond human comprehension. Some physicists have speculated that, under certain conditions, a parallel universe might emerge that is not just opposite in symmetry, but also fundamentally unstable. In such a scenario, a mirrored world might be dominated by chaotic forces, with physical laws constantly shifting in unpredictable ways. If such a realm existed, it would be a place of disorder, a cosmic opposite to the structured reality we know. If black holes are not just cosmic dead ends, but instead led somewhere, then it is possible that matter falling into a black hole in our universe is being ejected into a parallel one. In a mirror universe, these events might appear as the sudden formation of new matter, what some call white holes, theoretical objects that function as the reverse of black holes, spewing out material instead of drawing it in. Another possibility is that our universe and its twin are separated by an undetectable boundary. This barrier, if it exists, might occasionally weaken, allowing small disturbances to pass through. Such an event could appear in our universe as a seemingly random cosmic anomaly, an unexplained flash of energy, an unusual gravitational distortion, or a sudden shift in dark matter distribution. While there is no direct proof that a mirror universe exists, the concept remains a compelling solution to some of the deepest mysteries in physics. It offers an explanation for dark matter, a potential symmetry to balance the forces of nature, and even an answer to the question of what might lie beyond black holes. Quantum phantoms, when particles behave like ghosts. In the realm of quantum mechanics, things do not move in predictable paths, nor do they exist in only one place at a time. Instead, they flicker in and out of existence, their locations uncertain, their very nature fluid and shifting. They seem in many ways like ghosts, present yet not fully tangible, appearing where they should not be, disappearing before they can be fully grasped. One of the most famous examples of this strange behavior is the phenomenon known as quantum superposition. In the macroscopic world, an object must be in one place or another. A coin is either heads or tails. A door is either open or closed. But at the quantum level, particles exist in multiple states simultaneously. A single electron, for example, does not have a fixed position, but instead occupies a cloud of probabilities. It is only when it is measured, when it is interacted with, that the electron chooses a definite position. Until that moment, it is in a ghostly state of being both here and there at once. This uncertainty is not a result of technological limitations, but a fundamental aspect of quantum reality. The famous double-slit experiment demonstrates this in a way that remains unsettling even to physicists. When electrons are fired at a barrier with two slits, they behave as if they are waves, passing through both slits simultaneously and creating an interference pattern, as though each particle had split into multiple versions of itself. Yet if a detector is placed at the slits to observe which path the electrons take, they suddenly behave like individual particles, travelling through one slit or the other. The very act of observation collapses their ghostly state into something definite, as if reality itself only solidifies when it is being watched. Quantum entanglement is another phenomenon that gives the impression of something supernatural at play. When two particles become entangled, they remain linked no matter how far apart they are. A change in one particle instantly affects the other, even if they are on opposite sides of the universe. This connection seems to defy the limits of space and time, as if an invisible thread binds them together across vast distances. Albert Einstein famously called this spooky action at a distance, and despite extensive testing, no classical explanation has ever been found. It suggests that reality is woven together in ways that go beyond human understanding, with information travelling through hidden channels that do not obey conventional physics. In the everyday world, a ball rolling toward a hill will only reach the other side if it has enough energy to climb over. But in the quantum world, particles do not always follow such rules. They can sometimes pass through barriers as if they were never there, appearing on the other side without ever having crossed the space between. This is not a trick of illusion. It is a real and measurable effect called quantum tunneling, one that plays a crucial role in processes such as nuclear fusion in stars. Virtual particles take this eerie nature even further. According to quantum field theory, space is not truly empty, but rather a seething sea of fluctuations, where particles constantly pop into and out of existence. These ghost particles exist for only a fraction of a second before vanishing, but their brief presence is enough to exert measurable forces, affecting the behaviour of the universe itself. This has led some to speculate that even the vacuum of space is not truly empty, but is instead filled with ephemeral entities that appear and disappear too quickly to be seen. Perhaps the biggest mystery of quantum mechanics is wave function collapse, the idea that a particle's indefinite state solidifies only when it is measured. Some interpretations suggest that all possible outcomes exist simultaneously until an observation forces a single one into reality. This has led to theories such as the many worlds interpretation, which suggests that every quantum event creates a branching reality where each possible outcome plays out in a different universe. If this is true, then every moment of decision, every quantum fluctuation spawns an unseen world, forever splitting reality into an endless cascade of parallel possibilities. The question of why observation causes wave function collapse remains unanswered, and some theories propose that consciousness itself plays a role in shaping reality. This leads to unsettling questions. Does reality only become real when it is observed? If no one is watching, does the universe remain in a state of ghostly uncertainty? The quantum world is a place where nothing is truly solid, where existence itself is defined by probabilities, and where reality seems to flicker in and out of focus, like a mirage. It is a world that, despite all its scientific rigor, feels like something out of a ghost story. The dark side of dark matter. Could it harbor unseen life? Dark matter makes up roughly 85% of the universe's total mass, yet it cannot be seen, touched, or directly measured. It does not emit or reflect light, making it invisible to traditional telescopes. Scientists only know of its existence because of the way it interacts with gravity. Galaxies spin faster than they should, and galaxy clusters hold together more tightly than expected. Something unseen is exerting an immense gravitational pull, keeping the cosmic structure from unraveling. But what if dark matter is more than just a hidden mass? What if, rather than being a lifeless and passive substance, it harbors something unexpected, something alive? Life, as we know it, is based on ordinary matter, atoms, molecules, and chemical reactions that follow the rules of conventional physics. But dark matter does not appear to interact with the electromagnetic force, which means that atoms and molecules, as we understand them, cannot form within it. If dark matter hosts life, it must operate on a set of principles entirely separate from those governing visible matter. It might be composed of unknown particles, following a physics that remains beyond our reach. In our everyday reality, we are bound to 3 spatial dimensions, plus the passage of time. But some theories suggest that dark matter could exist in its own hidden dimensions, effectively making it a parallel world that shares the same space as our own, but never directly touches it. If this is true, then entire structures, or even entire civilizations, could exist right alongside us without ever interacting with the matter we perceive. If they exist, dark matter life forms might use entirely different means to process energy and sustain themselves. Just as our own bodies rely on organic compounds and electrical signals, dark matter beings could function through exotic forces that we do not yet understand. They might move, communicate, or even think using unknown interactions, guided by a physics that remains invisible to human instruments. Some researchers have speculated that dark matter might be capable of forming complex structures, similar to how ordinary matter can form atoms, molecules, and eventually planets and stars. If dark matter has its own set of forces, analogous to electromagnetism, but operating entirely within its own hidden realm, it could potentially clump together, forming vast unseen structures that mirror the galaxies we see in the visible universe. If this is the case, then dark matter galaxies, dark matter planets, and even dark matter life could be drifting through space alongside us, completely imperceptible to our senses. What if our own universe is teeming with life that we can never detect? Perhaps we are surrounded by dark matter creatures, civilizations, and ecosystems that coexist with our own reality, but remain forever out of reach. To them, we might be just as invisible, existing only as ghostly gravitational disturbances that subtly influence their own world. We may not be alone, yet we may never be able to prove otherwise. Some even propose that dark matter could form intelligent life, beings that are not just present, but aware. If an entire shadow universe exists, with its own complex structures, then intelligence may have evolved there as well. These hypothetical entities would not be bound by the limitations of visible matter. They might perceive the universe in ways we cannot imagine, existing outside the constraints of light, sound, and chemistry. If they have developed advanced technology, it would be completely undetectable by our instruments, operating through unknown principles that bypass our understanding of physics. Would dark matter civilizations ever attempt to contact us? And if they did, would we even recognize the signs? Our own scientific efforts to search for extraterrestrial life rely on radio waves, optical signals, and chemical signatures, all things based on visible matter. A dark matter civilization would likely have no reason to use such methods. Instead, they might attempt communication through gravitational effects, manipulating mass in ways that subtly distort the structure of the universe. If this is happening, we may already be seeing the results without realizing it. Hidden messages written in the way galaxies move, encoded in the unexplained behaviors of distant stars. There are some astrophysical anomalies that have yet to be fully explained. For instance, certain galaxies appear to lack dark matter entirely. while others seem to contain far more than expected. The distribution of dark matter across the cosmos is uneven, with strange voids and dense clumps that do not always match current models. While most of these inconsistencies are likely due to gaps in our understanding of cosmic evolution, some have suggested that they could be artificial, signs of an intelligence shaping the universe in ways we have yet to recognize. Some researchers have examined the behavior of dark matter around galaxy clusters and found odd distortions that do not align with current predictions. If an unknown force is at work, it could mean that dark matter is more dynamic than we realize. It could be shifting, changing, or even responding in ways that hint at a deeper complexity, perhaps even a form of intent. What are your thoughts about this kind of possibility? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.